So I'm going to
Good afternoon.
continue with the lecture on frequency modulation. Yeah. Okay, can you see my slide?
Yes, we can see you.
All right. So recall from last lecture where we talked about wideband FM. All right. So this slide basically show you the comparison between the wideband FM and narrowband FM. All right. So as far as modulation index is concerned, the wideband FM has a very big modulation index. Normally it's greater than 10, while the narrowband FM has a modulation index which is much smaller than 1. Right? And frequency deviation, again, frequency deviation for wideband FM again is very wide. All right, 75 kilohertz compared to narrowband FM, which is about 5 kilohertz only. And then for modulating frequency, which means the baseband signal frequency, the wideband FM basically can transmit any signal, baseband signal frequency from 30 hertz to 15 kilohertz. Yeah, whereas narrowband FM is suitable for baseband signal frequency that is less than 3 kilohertz. So you can see that less than 3 kilohertz is only the speech signal, all right, voice signal. And as far as the spectrum is concerned, the wideband FM theoretically has an infinite number of sidebands and carrier. One carrier and many sidebands, yeah, in theory. Whereas the narrowband FM has only 2 sidebands and a carrier itself. So this is very similar to a double sideband full carrier signal. And then for bandwidth, yeah, as the name wideband FM suggests, wideband FM normally has very wide bandwidth, which can be up to 15 times the bandwidth of a narrowband FM. All right. Whereas the narrowband FM bandwidth is similar to the double sideband full carrier bandwidth of 2 FM. So what is FM? FM is the highest modulating signal frequency. Yeah. So as far as noise suppression is concerned, all right, surprisingly, the wideband FM provide more suppression to noise. So you have less noise in the wideband FM as compared to in the narrowband FM. All right, that is due to the non-linear nature of the wideband FM system. And then so far for application, as far as application is concerned, wideband FM is widely used for entertainment and broadcasting. All right, so this is mainly for music as well as some good quality speech. Whereas narrowband FM is only suitable for speech. Yeah. So this is a list of specification for FM transmission. All right. So this table actually show you 4 types of commercial FM transmission. The first one is the commercial FM radio broadcast, right? The one that I don't know whether you still listen to or not. Yeah, the one FM, Mix FM, Hits FM, and so on. So this FM radio broadcast for Malaysia, the MCMC has allocated the frequency band 88 to 108 megahertz. All right, for this purpose. And then for each radio station, the bandwidth is 200 kilohertz. Yeah, and the maximum deviation allowed for each station or each channel is plus minus 75 kilohertz. All right, so this plus minus meaning is from the center frequency. So that actually make up the effective bandwidth of 150 kilohertz for each radio station. All right, but they are allocated 200 kilohertz. They can only use up to 150 kilohertz. All right, the other 50 kilohertz basically is the guide band on each side. All right, and then the highest audio frequency is up to 15 kilohertz. Yeah. And then for television sound, all right, and this is for analog television signal. I think no more, right? It used to be using the frequency band of 4.5 megahertz above the picture carrier frequency. Okay, channel bandwidth is a bit smaller, which is 100 kilohertz. So depend on whether the sound is transmitted as mono or stereo. So the deviation are different. Again, the highest audio signal can be up to 15 kilohertz. And then for public safety, right, such as the uh, communication between the police department, fire department, and taxis and whatever, the frequency band allocated, right, in Malaysia for this application is this range, 50 megahertz, and then from 122 to 174 megahertz. And each channel is allocated a bandwidth of 20 kilohertz, but then the maximum deviation again is plus minus 5 kilohertz. Yeah, that is to allow for a then guide band between each channel, between two adjacent channel. Highest audio frequency is 3 kilohertz, so therefore you can expect it can only transmit speech. And then for amateur radio use, the frequency band allocated is 260 megahertz to 470 megahertz. Yeah, channel bandwidth again is slightly smaller at 15 kilohertz. Maximum deviation plus minus 3. Highest audio is also only 3 kilohertz. So again, this is only for speech. Yeah. So again, for as far as this course is concerned, all right, you need to be aware of the various specifications for AM as well as for FM. All right. So in Malaysia, right, I talked about just now, in Malaysia commercial radio broadcasting, the band basically consists of 101 channel. All right, each channel again follow the, actually this is a standard international standard requirement. All right, so each of the channel is 200 kilohertz. Right, frequency is from 87.8 to 108. Center frequency running from 87.9 to 107.9. All right, so this picture basically show you some of the typical or the more popular FM radio station in Malaysia. All right, one FM, we need to tune in to 88.1, right, megahertz in order to receive one FM broadcast. So basically, this is a center frequency. And then Hits FM is centered at 92.9. All right, Mix FM 94.5 and so on. Which is your favorite radio station? Or do you still listen to radio station? Okay. All right. Let's talk about how FM signals are being generated. All right. There are two ways to generate FM signals. One way is to use the direct method. The other way is to use the indirect method. Right. So as far as direct method is concerned, there are two. The first one is double sideband suppressed carrier modulator. So basically, we use a multiplier. All right, and this will help you to generate the narrowband FM signal. To generate a wideband FM signal using direct method, we can actually use a voltage control oscillator, or VCO in short. Okay. However, the more popular way of generating wideband FM is the indirect method. All right, or in other words, we're going to look at the most popular indirect method, which is Armstrong method later on. Yeah, and the indirect method basically involves the generation of the wideband FM first, and then we change it to wideband FM. Okay, let's look at the direct method. The first direct method is making use of the double sideband suppressed carrier modulator. So this is only useful for generating narrowband FM signal, where the modulation index is very much smaller than 1. Right. So the modulator basically look like this. So we have now we have a message here. All right. And again, for this example, I'm going to make use of a message of a single tone. All right, given by this equation, which is a cosine signal. All right, so this message signal will be passed through an integrator. All right, passing through an integrator, then the output of the integrator, all right, will be multiplied by the, well, in fact, the double sideband suppressed carrier modulator is just a multiplier, isn't it? So this signal will then be multiplied with the phase shifted version of the carrier signal. All right, so we have a carrier signal here. Again, this carrier signal is just a cosine signal with the amplitude Vc. So after phase shifted, then it become a sine wave. All right. So similarly, if we integrate a cosine signal, we also get a sine signal, isn't it? So we multiply these two signals together. Then the output of the signal goes through a block, all right, with the gain K. All right, basically this is like the amplifier with the gain K. Okay. Then the output of the amplifier will then be added to a carrier. All right, added to the carrier, and then this will produce the narrowband FM signal. Hey, so how we prove that this is a narrowband FM signal then? Okay, taking the output of the phase shifter, right? The carrier signal is going to be this one, Vc sine omega Ct. And the output of the integrator is Vm over m sine omega mt, right? You integrate this cosine signal, you get this sine signal. Multiplying these two signal, all right, will give you, and then after you amplify it, then you give you a k Vm over omega. Vm omega come from here, Vm omega, all right? And then sine omega mt, which is this one here, and then a Vc sine omega Ct, which is the phase shifted version of your carrier signal. All right, again, if you look at this equation, is another case where you can apply your trigo identity, where this is sine x, this is sine y. All right, so sine x, sine y, the identity will be half of cos x minus y minus cos x plus y. All right, or their y x, well, doesn't matter lah, right? So it actually give you this two cosine term here. All right, so here basically I collect the terms. I get this k vm omega m, and then this vc I bring over because this is a constant, right? And then recall that k vm omega m basically is our modulation index, isn't it? All right, this will be modulation index. So that leaves us with VC and F over 2 multiply with the two sidebands. So this is the lower sideband and this is the upper sideband, right? Then we add these two signals together with the carrier signal. So that will give us the carrier here plus the two sidebands. All right, where the upper sideband basically is 180 degree out of phase. Right, so this is like, again, similar to your double sideband full carrier signal. Okay, and then for direct method, another direct method that is to make use of the voltage control oscillator. All right, this voltage control oscillator circuit basically produce an output frequency that is proportional to the voltage of the input signal. That's what we want, isn't it? Yeah, we want as far as FM signal is concerned, the change in the output frequency has to be proportional to the change in the amplitude of the input signal, right? So the VCO basically does that now. So and normally you can actually buy this, all right, in the form of IC, all right. Well, the benefit of this method is that you actually need less components. But again, because it's an IC, so therefore the output power normally is very low. So you need to amplify the signal. But the problem with amplification is the center frequency would then be drifted. All right. So when the center frequency drift, that means you won't be able to receive your radio station or at the frequency where it's defined. Right. So instead of 88.1, now you may have to tune to 88.15, or 88.2 in order to receive your radio station. Okay, let's talk about the more popular method here, which is the indirect method. All right. So in indirect method, we actually generate an FM signal using multiplication. All right, or we actually call frequency multiplication. We multiply the frequency. Okay. So in this method, again, we need to make use of the narrowband FM generator. We use it to actually generate a narrowband FM signal, right? Given baseband signal here, which is our message. And then after that, we pass the narrowband FM signal through a frequency multiplier. All right. So this frequency multiplier will actually increase the carrier frequency, all right, as well as increase the modulation index. All right. So how much you want to increase them depend on the multiplication factor of the frequency multiplier. All right. So if it's n, then you are able to increase the center frequency by n times and also the modulation index by n times. Yeah. So if you increase your modulation index, that means your narrowband FM now will become a wideband FM. Okay, so that's the concept of indirect generation of FM signal using multiplication technique. Yeah. So let's look into more details on how this can be done. So we're going to look at the Armstrong method. All right. So in Armstrong method, again, if you look at this, okay, I have some numbers here that can actually show you how the process actually happened. So we have a message signal here, all right, passing through a narrowband FM signal generator. So this narrowband FM signal generator will generate a narrowband FM signal with a carrier frequency 200 kilohertz, all right, and then a frequency deviation of 25 hertz. Okay, very small frequency deviation, only 25 hertz. Yeah. And then this signal, this narrowband FM signal, is then passed through a frequency multiplier that multiply the carrier frequency by 64 times and also multiply the frequency deviation by 64 times. All right. So the output of this multiplier will be a FM signal, all right, with the carrier frequency 12.8 megahertz and a frequency deviation of 1.6 kilohertz. Okay, remember the frequency multiplier will actually multiply the carrier frequency as well as multiply the frequency deviation. Okay, and in a lot of cases, the carrier frequency, all right, the multiplication factor required for the carrier frequency is not the same as the multiplication factor required on the frequency deviation. All right, because in this case, if you look at the final carrier frequency, which is 91.2 megahertz, all right, and the final frequency deviation, which is 76.8 kilohertz, you look at this, their factor are not the same. All right, so 91.2 meg, 91.2 meg divided by 200K, what is it? 91.2 meg, okay, divided by 200. So the multiplication factor here is, okay, this one need to multiply by 456 times, right? All right, where else the frequency deviation, which is 76.8 divided by 25. Okay, this is frequency deviation is 3,702 times, right? So that means we cannot just simply feed the signal through a frequency multiplier, yeah, because the carrier frequency need a lower multiplication factor as compared to the frequency deviation here. So to actually reduce the multiplication factor on the carrier frequency, we actually make use of a mixer, a frequency mixer here. All right, so this frequency mixer or called frequency converter basically is to shift down the carrier frequency. All right, reduce the carrier frequency. And the good thing about this frequency mixer is it does not change our frequency deviation. All right, you only change the carrier frequency, but not the frequency deviation. So in this example here, we make use of, again, a crystal oscillator that generate a local, we generate a frequency of 10.9 megahertz. All right, so 10.9 megahertz. So this signal we multiply with the signal that come out from this frequency multiplier. Okay, so again, if you look at the frequency mixer, it's the same as our double sideband suppressed carrier modulator, isn't it? Right? We multiply signal, two signals of different frequency. So when we multiply two signals of different frequency, what will be the output? Here, the output here. The output here will be FC2 plus minus FLO, isn't it? Right? FC2 plus minus FLO, right? Just like your FC plus minus FM, right? You have two frequency, upper sideband and lower sideband frequency. So it's the same here. All right. So we multiply this signal with the frequency 12.8 megahertz with another signal with of frequency 10.9 megahertz. So we're going to end up with two signals. All right, we're going to end up with two signals. So 12.8 minus 10.9. All right, that will give you a signal of 1.9 kilohertz. Here will be 1.9 megahertz. No. Another one will be 12.8 plus 10.9. Right, there another one will be 23.7 megahertz. All right, remember we want to shift down our carrier frequency, right? So therefore, we make use of a bandpass filter here to actually allow only the signal with frequency 1.9 megahertz to pass. All right, so therefore, the output of the bandpass filter will be FM signal where the carrier frequency is 1.9 megahertz. All right, frequency deviation no change, 1.6 kilohertz. All right, then we pass this signal through another frequency multiplier that multiply the frequency and the deviation by 48 times. All right, 48 times here. And then 1.9 multiplied with 48, you get 91.2. All right, and then 1.6 multiplied with 48, you get 76.8. So you get the exact frequency deviation that is required for the wideband FM. And also the carrier frequency of 91.2 megahertz for this wideband FM station. Okay, so the benefit of using this system or Armstrong method is that The generation of FM or narrowband FM is actually very straightforward. So the component required actually is very minimum. And then this narrowband FM has low modulation index, right? And it, because of the low modulation index that is used, so the distortion basically again will be low as well. Yeah. And generation of narrowband FM at low frequency here, which is only 200 kilohertz, instead of straightway generating a signal at 91.2 megahertz from a baseband of maybe 10 kilohertz, is actually more stable. All right, your narrowband FM signal at this point is actually more stable. Then after that only you multiply. All right. But the problem with too much multiplication actually will give you some excess noise. So that is something that you need to be aware of. Okay. Are you still with me?
Yeah. Can.
Okay. All right, these numbers, you actually have to work out one by one. So I'm going to show you how to work out this number with the example here. All right. So in this example, we are asked to design an Armstrong indirect FM modulator. All right. To generate an FM signal with carrier frequency 97.3 megahertz and a frequency deviation of 10.24 kilohertz. All right. Meaning at the end here, we need to have a FM signal with a carrier frequency 97.3 megahertz and a frequency deviation of 10.24 kilohertz. We have a narrowband FM generator that gives us a carrier frequency of 20 kilohertz and a deviation of 5 hertz. All right, so meaning we have this block here. All right, this block is able to produce a narrowband FM signal with a carrier frequency 20 kilohertz and a frequency deviation of 5 hertz. All right, so in this case, you can only use frequency doublers. All right, what is frequency doublers? Frequency doublers are circuit that actually only double your frequency every time you use it. All right, meaning and then for frequency multiplication, you can actually cascade. You can actually cascade the blocks. All right, so that means in this case, if you're allowed to use only frequency doublers, all right, each frequency doubler basically multiply your frequency by 2. All right. So if you need to multiply the frequency by, let's say 8 times, then you just cascade 3 of them. All right. So meaning you have times 2, and then you times 2 again, and then you times 2 again. So that will give you this is your F1, then this is your F2. Basically your F2 will be 8 times F1. All right, so that's what's meant by frequency doublers. You can only have you can only use these doublers. So if let's say you need to multiply your frequency by 64 times, then you just cascade 6 of these, right? So additionally, a local oscillator with adjustable frequency between 400 to 500 kilohertz is available for frequency mixing. All right, so what it means here, your FLO is actually between 400K to 500 kilohertz. All right, so you can actually adjust the frequency to the exact frequency that you need. All right, to generate a final carrier frequency of 97.3 meg and a final frequency deviation of 10.24 kilohertz. Okay, so as far as Armstrong indirect FM modulator is concerned, okay, this is the standard block. This diagram basically show you the standard block, all right? So we make use of, we're going to pass our signal, let's say MT, into a narrowband FM modulator, right, to give us the first or the narrowband FM signal. Then we do a multiplication on the FM signal. This is our first stage multiplier. All right, stage 1 multiplier. I call it N1. All right. So this stage 1 multiplier is going to give me a FM signal with the carrier frequency FC2. All right, and the frequency deviation of delta F2. All right, so how is FC2 related to FC1? So basically FC2 is equals to N1 FC1, right? And delta F2 is equals to N1 delta F1, right? Because the frequency multiplier will will produce an output, all right, that of a factor N1 times the input frequency, all right, which is FC1, and also N1 times the frequency deviation, which is delta F1. Okay, then we mix the signal with the signal coming out from a local oscillator here, which is this one here. That gives us FC3. All right. But then the FC3, your FC3 here, can be, all right, can be many how to say, okay, it can consist of two frequency components. All right. So the frequency component can be FC2 plus or minus FLO, right, which I talked about just now, right? Yeah. In fact, this FC3 can also be FLO plus minus FC2. Correct or not? It's actually the difference between these two frequencies. Yeah. Then as far as the delta F3 is concerned, all right, the mixer here does not change the frequency deviation. So delta F3 is still the same as delta F2. All right. Then we pass this signal through a bandpass filter, all right, to allow any one of these four frequencies component to pass. Okay, so FC4 is as any one of these four. All right. So if you choose the appropriate FC4, yeah, and then you multiply it with the second multiplier, which is N2 here, that is supposed to give you a FC5, which is 97.3 megahertz. Yeah, and same thing, your delta F4. Basically, delta F4 is the same as delta F3, isn't it? Because bandpass filter will not change your frequency deviation of your signal. All right. So basically, delta F4 is same as delta F3, okay, which is the same as delta F2. All right, and what is delta F2? Delta F2 basically is N1 delta F1. Right. So if you multiply this frequency deviation again by a factor of N2, all right, it should give you the final frequency deviation delta F5 of 10.24 kilohertz. Okay, so that's the whole idea behind the Armstrong indirect FM generation. All right, so with this in mind, then let's put down our first equation here, which is delta F5 is actually N2 times of delta F4, right? Which is N2 times of delta F3, which is N2 times of delta F2, all right, where delta F2 basically is N1 delta F1. So delta F5 is N2 N1 delta F1, right? So this is our first equation here. And then from this equation, well, if you rearrange, then you get N2 N1 basically is equals to delta F5 divided by delta F1. All right. So we know what is delta F5, isn't it? Delta F5 is 10.24 kilohertz. And delta F1 is 5 hertz, right? Then that gives us N2, N1 of 2048. All right, 2048. Yeah. So again, I won't say that is first equation. Use this as your first equation. Okay, this one. Now, after the mixer, all right, after the mixer here, this mixer FC3, I mentioned just now, FC3 basically is the difference between the two input frequency. So, or the sum. Yeah, so it can be FLO plus minus FC2 or FC2 plus minus FLO. All right, so it can be either of these. So the FC4 can be either one of these four frequency. All right, because FC4 is a bandpass version of FC3. All right, we have to design our bandpass filter so that it allow only one of these four frequency component to pass. Okay, all the four are actually the same signal, just that they are actually using different carrier frequency. That's all. Yeah. So moving on. So now we do not know which is correct FC4 that we should select. So we have to actually try some of the numbers. Okay. So let's try FC4 is equals to FLO minus FC2. Let's try this expression. All right. So what is FC2? FC2 is N1 FC1, right? So again, link it to, we only know FC5 and FC1, right? So link FC4 to FC5. So FC5 basically is N2 FC4, right? N2 FC4. And now let's put the expression for FC4 into this equation. So FC4 is FLO minus FC2. So FC2 is N1 FC1. So both multiplied by a factor of N2. So you have N2 FLO minus N2 N1 FC1. All right. Now, rearrange your equation. Rearrange your equation because we want to find N2 first. All right. So N2 is equals to FC5 plus N2 N1 FC1 divided by FLO. All right. If you arrange this equation over here. And substituting the value for all the known items, FC5 is 97.3 meg, N2, N1 is 2048, right? FC1 is 20 kilohertz. Okay, divided by FLO. What is FLO? We know FLO is somewhere between 400K to 500K. All right, divided by a number which is between 400 to 500K. All right, so if you do this, you divide this by 400K, you will get 400K, you'll get a number which is 345.65. All right, and if you to divide the numerator by 500K, you will get a number is 276.52. All right, so within this range of numbers, all right, here it must be a factor of 2. All right, you must find a number that is a factor of 2 in this range, right? Which means it has to be something 2 to the power of x. All right. However, in this range, you won't be able to find any numbers. All right, because 2 to the power of 8 will give you 256, right? And then 2 to the power of 9 will give you 512, isn't it? So there is no number that can fit. There is no N2 that can fit this range. Okay, so that means this F4 equation is not suitable. Cannot use this. All right. So I'm going to try another expression for FC4 here. So I'm going to use FC4 as FLO plus FC2. All right, so instead of shifting down the frequency of FC2, I'm going to shift up the frequency of FC2. All right, So in this case, again, substituting the expression for FC2 into this equation, and then move on to find FC5. All right, and then rearrange the entire equation so that you look for N2. Okay, so what you have here is again 97.3 meg. Now it's minus, instead of plus, now it's minus. All right, 2048 times 20k divided by 400 to 500k. So if you were to do this, all right, divide the numerator by 400k, you're going to get 140.85. Okay, divide it by 500k, you're going to get 112.68. All right, so within this range of numbers, there is one number that fit our requirement, which is 2 to the power of 7. All right, 2 to the power 7 give you 128. All right, so therefore, we found our N2, which is 128. All right, so with N2 being 128, then N1 is just 2048 divided by 128. So that will give us an N1 of 16. All right, so we know now our N1 is 16. Our N2 is 128. All right, so now we need to find what the local oscillator frequency is. All right, so to find FLO, substituting the N2 back into this equation. All right, so this equation, you make use of this equation, you rearrange, you bring your N2 on to this side, you bring your you bring your N2 over here, and then you bring your FLO over here. You just swap your N2 with FLO, then you get your FLO is equals to FC5 minus N2 N1 FC1 divided by N2. All right, so substituting the values of all the known items into this equation, you get your local oscillator frequency is 440156.25 Hertz. All right, so this is okay because you can tune, right? Because the FLO given, you can actually tune between 400k to 500k. All right, so you're going to tune to 440156.25, which is okay. All right. Then what kind of bandpass filter can you use over here then? All right, to find out the bandpass filter requirement, then you need to know your FC4. All right, so now putting back your FLO and FC2 into this equation here will bring you FC4. All right, so FLO is 440156.25 plus N1 FC1. Okay, FC2 basically is N1 FC1. So N1 is 16, FC1 is 20k. So that will give you a FC4 of 760,156.25 Hertz. Okay, so you know that your bandpass filter need to center at this frequency. Okay, your bandpass filter basically need to center at FC4. And what is the pass band then? All right, to know your pass band, you need to know what is your delta F4. All right, delta F4 will give you the pass band for your bandpass filter. All right, so delta F4 basically is same as delta F3, same as delta F2, is same as N1 F1, right? N1 F1, so N1 is 16, delta F1, sorry, N1 delta F1. So N1 is 16, delta F1 is 5, so that gives us the delta F4 of 80 Hertz. All right, 80 Hertz. So therefore, your bandpass filter need to have its center frequency at this, which is your FC4, with a pass band of 2 times your delta F4, which is 160 Hertz. All right, so what it means is your bandpass filter need to be this one here. So this is your FC4. All right, this one is your delta F4. All right, so again, so your entire pass band will be 2 times delta F4. Okay. Are you still with me?
Oh, yes, yes.
All right. So with this, you can actually try, I think the last two tutorial questions, all right, in your tutorial sheet. Yeah, I give you some time to digest. In case you have a question, then you may ask now. Okay, so when you're asked to design Armstrong FM modulator, all right, I think the most difficult part is to find the correct FC4, isn't it? Because there are 4 possibilities there. And how do you know which one is suitable? Okay, you can use try and error, but that is going to, like in this case here, you can see if the first one doesn't work, then I have to try a second one, right? If the second one doesn't work, I may have to try the third one, which is FC2 minus FLO, or the fourth one, which is FC2 plus FLO. All right. So one clue that you can reduce the trial that you need to perform is you take FC5 divide by FC1. Right, in this case, it's 97.3 meg divided by 20K. So it gives you a factor of 4865. All right. And then you try again, divide your delta F5 with delta F1. So this is 10.24K divided by 5. Right. So 10.25K divided by 5 will give you a factor of 2050. All right. So in this example, you can see that the multiplication factor required for the carrier frequency is higher than the multiplication factor required for your frequency deviation. All right. So that means your mixer here need to increase your FC2, increase this frequency. All right. That means your FC3 need to be higher than FC2. All right. FC3 need to be higher than FC2. And therefore, it has to be plus. All right. One of the plus equation. Which is different from this example here. All right. If you look at this example here, in this example, the multiplication for carrier frequency is lower than the multiplication factor for the frequency deviation. And therefore, your mixer output or the bandpass filter need to give you a FC4 that is low. Okay, that is lower than the input frequency. You need to shift down. All right, so therefore here the minus equation is actually better. In this case, we take 1.9 because there is FC2 minus FLO. All right. So again, if you compare the multiplication factor here, that should give you an idea whether you should use plus or you should use minus. Okay. I will move into demodulation because we only have what about 7 minutes left. I'll give you some time to digest in case you have questions.
Miss,
Yeah.
I want to ask the whole system for this is the whole system for this example 6 is the complexity in the frequency multiplicator and the frequency load, right?
Frequency multiplier
And the load adjustable frequency between got a range, the FLD right there. Yes.
If I understand your question correctly, you're asking about when you're asked to design what you need to do, right?
Yes.
Is that your question? Okay.
Yes.
All right. When you're asked to design an Armstrong FM modulator, all right. Basically, what you need to do is you need to identify what is your N1. You need to identify what is your N2. You need to identify what is the FLO. You also need to identify what kind of bandpass filter you need. The block diagram is the same. All right. As far as the block diagram concerned, the block diagram is the same. You may be required to look for a correct or suitable narrowband FM signal generator as well. Okay. If that is not given, then if it's given, then it's very easy. You just need to find all these intermediate blocks. Mixer is just a multiplier. That's all. Nothing special about it. Does that answer your question?
So it doesn't matter if it got mentioned how many multiplier they need, for the designing question one.
Okay, the standard is to make use of two-stage multiplication, which is N1 and N2. All right, and then in N1 and N2, N1 itself, all right, it can be many multiplier blocks. So in this case, we found our N1 as what? N1 is 16, isn't it? All right, N1 is 16. So how do you construct N1? You construct N1 by times 2, times 2, times 2, times 2, right? So you actually use 4 frequency doubler here, isn't it?
Yes.
Yes. All right. And then for N2, the second stage multiplication, this is 2 to the power of 7. Therefore, you use 7 frequency doublers. You cascade them now. Right. This is times 2, and so on. That's why the question says here only frequency doublers can be used. All right, so therefore the difficulty here is to find a value for N1 and N2 that can satisfy this condition.
Okay, answer my question.
Yeah,
Answer my
okay.
question.
Good. And then for your tutorial questions, I actually mentioned, I think there's one question that say you can use doublers, you can use triplets, you can use quintuplets and so on. Then I think it's not so stringent anymore. That means you can let me try to open the. I stopped sharing already. Is that okay? So I'm going to end
No
my.
problem.
I hope you got down what is written. Okay, let me see whether I can. The tutorial question. Tutorial 3. Okay. Okay, if you look at your tutorial 3, I think the last 2 questions basically ask you to design the Armstrong indirect FM modulator. All right. this one, again, the final carrier frequency is 96 megahertz. Deviation is 20 kilohertz. You have a narrowband FM generator with a carrier frequency 200 kilohertz, adjustable delta F in a range of 99 to 10 hertz. Okay, and so in this case, the difficulty is you need to find the correct delta F. All right, that you need at the narrowband FM generator. So again, the oscillator frequency is somewhere between 9 to 10 megahertz. All right, bandpass filter with any center frequency, and only frequency doublers are available. So that means you can only use frequency doublers here, all the times 2, times 2, and times 2. Okay, about question 10. Question 10 now, yeah, question 10 now, you can use frequency doublers, you can use triplets, and you can also use frequency quintuplets, which is times 5. All right, so you can mix. All right, you can mix. Meaning if you need to multiply the frequency by 10 times, then you use one doublers and with one quintuplets. 2 times 5 will give you 10, isn't it? Yeah. And let's say you need 30. So you need a multiplication factor of 30, 30. Then what you do is you just cascade times 2 with the times 3 with the times 5. Then 2 times 3 is 6. 6 times 5 is 30. All right, so this is another example. All right, so the best way to check your understanding is actually by using it. Okay, all right. Are there any other questions?
No question.
No question. So therefore, we're going to end the class now. So for those who have questions too shy to ask, then you may want to stay back. I'll wait for you for a while, and then you may ask. Okay, if not, then we're going to end the class here then.
Thank you, Miss.
All right, thank you.